All right. What we're going to do right now is we're going to go through some derivatives of the various functions to make sure that we can solve um, various types of derivatives, whether it's involving trig inverses and exponentials and trigonometric ones and whatnot. So what we're going to do is we're going to take the derivative of a bunch of different functions. We'll do like 5. So first off, let's try the derivative of, we have r equals tangent squared of 3 minus theta squared. All right, let's find the derivative of this function. So we'll take this with respect to r. And what we have then is r prime. And remember, we have to use a chain rule. Okay, this is the same thing as writing when we had this function as tangent of 3 minus theta squared. Actually, this should be a theta. All right, squared, and that quantity squared. Okay, so what we have then is going to be 2. We're going to have the tangent of 3 minus theta squared. And then we're going to take the derivative of tangent, which we know is secant squared of 3 minus theta squared, and then times the derivative of the inside, which will be negative 2 theta. From here, we can simplify a little bit. So we can say negative 4 theta. And then we have our tangent of 3 minus theta, the quantity squared. And we have secant squared of 3 minus squared right there. And that would be our theta. All right, well, let's find some more derivatives. And what we have right here, let's try this one. And we'll go with, I don't know, y equals natural log of the square root of x. All right, this is a little easier one. We have this, I'm going to simplify this a little, use probably logs. We have natural log of x to 1/2. And we can use the property of logs by putting 1/2 natural log of x. So now we'll take the derivative of this with respect to x. All right, here. And so we have y prime. And we'll have 1/2 times the derivative of natural log of x, which is 1 over x, where we can get 1 over 2x. All right, that was a simple one. That was kind of fun. Let's try another one. Here, I'll turn to blue. From here, let's go with, let's see. Let's have y equals x to the natural log of x. Try this one? Sure, why not? With this, we're going to solve this, and notice what we have right here is we have y and x natural log of x. With this one, we have a base and exponent, both of the variables, so we can't solve it that way using normal derivative properties. So we're going to first change this around a little bit by natural logging both sides. When we do that, we can now use the properties of logs, and we can move that natural log of x in front, and now we have natural log of x times natural log of x. All right, which actually is natural log of x squared. So now we have natural log of x squared. All right. Now from here, we have y is now we can take the derivative with respect to x, both sides, of 1 over y prime. We have 2 natural log of x times the inside, which is 1 over x. We can simplify this now, so we have y prime equals 2 natural log of x over x times y. Well, let's substitute what y is, and we remember y is equal to x natural log of x. So we have 2 natural log of x over x times x to the natural log of x. That equals y prime. So using log differentiation, we can get that answer. All right, cool. Let's try another one, shall we? All right, and we have this. And we'll go with, I don't know, we'll have r equals log base 2 of theta squared. We'll do one with a log of a base other than e. And we'll take this to theta. So we got r prime. Now from here, we're going to take with a different base. When we have solved this, we're going to have to go and go 1 over, all right, and we have theta squared, times the natural log of the base, which is 2. And this can be multiplied now by the derivative of our inside, which is 2 theta. And we'll simplify this a little bit. And we can have, all right, 2 on top. This and this will turn to 1. So we have theta times natural log of 2, r prime. And that would be our solution. Okay, we'll go one more just for good measure. We'll do an inverse trig one. And let's check out this one. We'll take y equals inverse sine of 1 minus u squared. And we'll take the derivative of this with respect to u. All right. Now, just so you know, inverse sine is the same thing as arc sine. 1 minus u squared equal y. So they're all in the same. So we're taking the derivative of arc sine, which is the inverse sine. Okay. So that is not the reciprocal. So when you see this, that is not the reciprocal. That is actually arc sine. So now, in solving this, we're going to take the derivative of inverse sine. And what we have is y prime equals the inverse sine of x, which is 1 over square root of, and give me 1 second. What we have right here, sorry about that, is we're going to have 1 minus now the quantity, whatever inside here. All right, and this is what our u is. So we can use chain rule, and we have the square root of 1 minus u squared. Okay, times now the derivative of the inside, so we have 1/2, using the finish of the chain rule, and that's the negative 1/2 power, times derivative of the inside of that, which is negative 2u. All right, so simplifying this a little bit, we realize that this right here will cancel out, and we have that in the bottom. So we have, it appears to be negative u, and right here we're going to have the square root of 1 minus u squared times the square root of 1 minus quantity square root of 1 minus u squared, which will just simply be 1 minus u squared. They're squaring the square root right here. All right, that's square, so that's going to cancel out. And we can go like so. Since we have both the same square root, all right, we can simplify this a little bit more. And we can actually put this all under 1 square root. And what we have then is the square root of 1 minus squared. And what we have then is this times this cancels out the negative u. So find a little farther, and what we have then is the square root of negative u plus u cubed. All right, and that would be a simplified answer if we wanted to go that far. All right, I don't know if this, hopefully this has helped you. I think I'm going to do one more just for fun. It's another inverse trig one, and it looks like fun. But we'll try this one. Y equals cosecant, inverse cosecant of secant of x. And with this one right here, and we are going to use the values of x between 0 and 2 pi. So we'll have that. All right, now, finding this one, we have inverse secant. So, or cosecant, that is. And we're going to take the derivative of this with respect to x. So what we have is y prime. And now we're going to have 1 over. Now with a cosecant, this is going to be negative. And cosecant is very similar to what we have with secant, except it's going to be the opposite. So what we have right here is going to be 1 over u, or our inside, this is our u. So it'll be secant of x, which is value. We have the square root then of that secant, which is going to be squared. And then we're going to have minus 1. Times the derivative of our u, which is going to be times the derivative of secant, which we know is going to be tangent of x, secant of x. That right there. From here, we can see that this and this will cancel out. And what we have then is 1 over or negative tangent of x, bring that over there, and we have secant square root of x minus 1. Okay, and from that right there, we can maybe simplify a little bit farther, but we'll just keep it like so and right there. Okay, so once again, hope this has helped you out on how to do some different various derivatives with inverse trig and with logs and exponents and using log differentiation. All right, good luck. Happy differentiating.